All right, thanks for the introduction. And good morning, folks. Welcome to this presentation. The topic I bring here today is understanding the performance of DPDK as a computer architect. There are multiple contributors to this work. This is a joint work between University of Massachusetts, Lowell, and Intel Corporation. The first three authors, Xiaoban Wu, Peilong Li, myself, and Yan Luo are with UMass. Larry Wan, Mark Papin, and John Morgan are with Intel. As a team with both DPDK users and developers, we feel it's important to bring up this topic to the huge community. And I assume everyone here today is with network background, right? So let me try this. The great joke about TCP is that everyone will get them, okay? I see some smiling faces. So as a network guy, we tend to think network. But sometimes it is more precise and important to think from other perspectives. So this work is trying to give you a new angle, understanding the performance of DPDK from a computer architect perspective. So first of all, this is a quick agenda of my talk today. We will first touch on the background and motivations of this work, and then I will introduce some basic knowledge about OVS architecture and memory hierarchies, and then I will talk about the experiment setup and as well as the test methodologies. And then I'll give you the performance evaluation between the vanilla OVS versus the OVS DPDK. And then we'll talk about the MultiSocket platform impact analysis. And then finally, we will reach the conclusion and some key takeaways. All right. So for a typical data center and a cloud, it is highly relying on the virtualization technology in order to fully utilize the hardware. So in this case, the Open vSwitch is a key connectivity component in the cloud and data center to provide the network of this virtualized hardware. There are some good examples like OpenStack and OpenNebula. But the problem is, as the line rate keep increasing from 10 gig to all the way to 100 gig, the OVS is hard to keep up with the speed. So that's why Intel released the DPDK accelerated version of OVS in order to fix this issue. Okay. So, but we all know that from all these 2 days, we have been seeing a lot of fancy talks talking about the performance is higher than the vanilla OVS, but why? What is the magic behind this? So in this work, we're trying to explain the reason from a new angle. And we will talk about the cache behaviors of these two softwares and the contact switches, something like that. So I prepared a couple of slides to do the introduction, just in case everybody is on the same page. This is a typical application scenario of OVS in cloud and data center. And we can see on this figure, we have the physical racks connected by the physical switches. And on each of these physical rack, we have multiple virtual machines. And all those virtual machines are connected with our virtual switches. And OVS and virtual machine can talk with other VMs via the virtual NICs, and it can talk with other physical racks over the physical NICs. And if we zoom into one typical component in this diagram, we'll have a more detailed view. Okay, so in this diagram on the right-hand side, it contains two domains: one user domain, one kernel domain. And in the user domain, we have the virtual machine, which it contains the virtual Ethernet port, VirtIO driver, etc. And in the kernel space, we have the Open vSwitch, the tabs, and the vhost. We can observe two basic communication scenarios from this diagram. The first one is if two virtual machines trying to communicate with each other, they can go either within one physical rack, that is the first case, VM to vNIC to virtual machine, or in another case, they can go out of this hardware to another hardware, that is VM to physical NIC to another virtual machine. We will talk more about these two scenarios in our evaluation. Basically, our test environment is built upon this. And another I/O comparison between OVS and OVS DPDK. So if you see on the left-hand side, this is an OVS data path. Okay, again, we have user space, kernel space, and for a vanilla OVS, it contains typically two basic components. One reside in the kernel space that our kernel module, and one OVS daemon running in the user space. Okay, so for a typical data path, it will go from one virtual machine to the kernel module and go to somewhere else, to the outside world. And if the rule is not cached in the kernel, then obviously it has to go ask for the daemon and then gather rules. So this will involve a lot of contact switches, the user to kernel contact switches. We will give you some concrete analysis on this case in later slices. But if you look at the right-hand side, that's the OVS DPDK version. And we can see that OVS DPDK has its own implementation of the data path. Okay? It has the virtual switch forwarding plane and also the PUMO driver. So it can either stay within the user space by, the data path will go through the vSwitch forwarding plane, or if it wants to talk to the outside world, it can go bypass the kernel to the physical NIC. Okay. Either of this case will not involve much user kernel space contact switches. And again, we will give you the numbers for it. So some college knowledge again. For a typical processor, we have multiple cores. And for each core, we have L1 cache, L2 cache, which is private. And then we have shared space, the L3 cache or last level cache, LLC. And then we can go to the memory. And we know that the further we go away from the core, the more latency we will have. And we take the numbers from the typical Intel Skylake processor, and you can see the number in the table. If you see these L2 data access latency to L3 and to memory, you can see the number will increase from 12 to 44 all the way to 140 with 2 gigahertz example. And also the bandwidth of this communication will decrease if you go in further, as we can see from the numbers. So based on this discussion, this is our testbed setup. Okay, we have two categories. One is the gas-to-gas communication case. We call it VM to VM communication. In this case, we have one physical host running two virtual machines. And these two virtual machines will talk with each other over OVS or OVS DPDK. Okay, this is the first category. And in the second category, we have the guest to host communication, or in our case, we call it VM to host. Okay, so again, we have two physical hosts. One physical host has one single virtual machine and running either OVS or OVS DPDK. Another virtual host will run as the iPerf server, okay? And the benchmark we're using is iPerf. So in either of these two categories, we have iPerf server, iPerf client talking to each other. Okay. So we test this setup based on this hardware specifications. We use the Intel Supermicro server with a Xeon D 8-core processor, each running at 2 gigahertz. It has L1 cache, L2 cache, last level cache, and memory. Right? And the physical NIC we're using is an Intel 10G NIC. And it is running Ubuntu 16.04 and OVS versions 2.5.0. DPDK version is 16.04. So all the VMs, as you can see on the previous slide, are created by KVM and emulated by QEMU. And we run iPerf tests on the provided environment. And we use some profiling tools to gather data. One is the Linux perf, and one is the Intel VTune amplifier. And just out of curiosity, how many of you are using VTune amplifier for your projects? Good, good. I see a couple of hands. So this is a very good tool that you can track back to your source code and do some fancy, performance profiling. So iPerf test is running on this, is running as such. So 4 different experiments. We have one iPerf server, iPerf client, and the only difference between these 4 is it either VM to VM talk, or is it either OVS or OVS DPDK? So 4 different cases. And now, this is the first evaluation. In this slide, we are trying to give you an expression between the throughput and IPC performance. IPC stands for instructions per cycle. Okay, that is a computer architect term. So on the x-axis, we can see 4 different cases. From left to right, that is VM to VM or VM to host over OVS, the first 2. And the right-hand 2 are OVS DPDK cases. Okay, it is either VM to VM communication or VM to host communication, the last one. And the y-axis stands for the exact number in different unit. Okay, so if you look at the blue bars, that is the throughput comparison. And we can see if we compare the first blue bar with the third blue bar, that is the comparison between OVS and OVS DPDK with the VM to VM communication case. Okay, we can see a 5.5 times more throughput increase for this scenario. And if we compare the second and the fourth blue bars, then that's the VM to host cases. And we can observe at least a 3 times more throughput increase. Okay, so if we look at the orange bars, that stands for the IPC number. Okay, so for a typical 4-issue architecture, we know that the ideal IPC is 4. Okay, so if we are not using the OVS DPDK, then the IPC is much lower than 1, which is like 0.3 or 0.2, something like that. Okay, but for the OVS DPDK cases, this number is much higher. It's like 3 to 4 times higher, and it's bigger than 1. Okay, so I believe the key takeaway from this figure is that if using OVS DPDK, we can observe up to 4.5 times more throughput speed up. And also the IPC is like 4 times more as well. The second evaluation is about the cache behavior. So again, on the x-axis, that's 4 different scenarios. And on the y-axis, that's the exact number in different unit. So the left y-axis stands for the cache reference in the unit of million reference per second. And the y-axis stands for the L1 D-cache miss rate. Okay, so if we look at the blue bars, again, we compare the first bar and the third bar, we can observe at least 7 times more cache references. And if we look at the second and the fourth bar, and that is like 8 times more cache references. Okay, that means if we're using OVS DPDK, cache is more cache friendly, and we can have more cache references. And if we look at the cache L1 D cache miss rate, then we can observe that for the second and fourth bar, for the second and fourth dot, that is like 50% decrease. Okay, so the key takeaway from this figure is that if we are using OVS DPDK, then we will have more cache references and fewer L1 cache misses. And this is because of the software prefetching mechanism designed in DPDK. Okay, the third evaluation is about the last level cache and also the TLB buffer. Okay, so, and again, the y-axis stands for different 4 scenarios, and the y-axis this time is normalized number, okay? So the unit for blue bars and orange bars are the reference rate, which is million per cycle. So we divide all these numbers by the first group. So you can see the first group are all normalized to 1. Okay? So if we look at the LLC performance, then we can observe a 3 to 6 times more access with the OVS DPDK cases. Okay? And if we look at the yellow bars, which stand for the data TLB miss rate, we can see, surprisingly, if you're using OVS DPDK, the TLB miss rate is almost 0. It's only a little bit edge over 0, but almost 0. So with this slide, the key takeaway from here is if we're using OVS DPDK, then we will have more LLC access, and we will have near 0 TLB miss. Okay? And this is thanks to the design of this huge page. Okay? In this case, we won't have too many TLB miss, and we won't be penalized with the page walk, which is very expensive. And later on, we figure out that a cross-socket communication might be very interesting, because modern data centers will employ many socket platform, which is used to design scalability within the power budget. So the question is, how does the vanilla OVS and the OVS DPDK behave on such multi-socket platform? Okay, this might be a very interesting topic. And this time we use a different hardware setup. We use a 2-socket server. Okay, and each of these sockets has a Xeon E5 processor on it, which contains 6 cores, each core running at 3.4 gigahertz. And it contains L1 cache, L2 cache, last level cache, and also the memories. Okay? So with this hardware, we again have 4 different setups, 4 different configurations. As you can see on the figure, that's 2 configuration categories. In the first category, that is within one socket communication. So basically, we have 2 VMs reside on one socket, and these two VMs will communicate with each other over OVS or OVS DPDK. And in the second category, we have two VMs running affinitized to two different sockets. And these two VMs will talk with each other over OVS or OVS DPDK. And again, we run iPerf benchmark for each of these four configurations. So this diagram contains a lot of information. And basically, this is a throughput comparison and cache behavior comparison. Okay, so again, on the x-axis, these are the four different configurations. You can see from the left-hand side to the right-hand side, that is OVS on the same socket, OVS on the different socket, and OVS DPDK on the same socket or OVS on the different socket. Okay? And y-axis stands for the exact number with different unit. If we look at the blue bars, which stand for the throughput, then we can observe if we compare the first group blue bar and the second blue bar, that is like 1.3 times more throughput decrease if we are using different socket. And likewise, if we compare the third blue bar with the fourth blue bar, again, we can see a decrease of the throughput. That means cross-socket design will actually affect your performance negatively. Okay? And if we look at the cache reference, the LLC cache references, which is the gray bar and the yellow bar, we can see the cache references will actually be less if we are running on different socket. Okay? So I believe the key takeaway from here is if we have multiple socket platform, then a more widely used way is to run on the same socket if you have very high bandwidth communication. So for the same socket case, you will have higher bandwidth and also better LLC behavior. And if you remember in our introduction slides, we talk about the contact switches for OVS and OVS DPDK. And this diagram is to show you the data. So if we compare this first group with the second group, you can see OVS DPDK contact switches will drop dramatically. It's like 4 to 5 times less contact switches. And if we look at same socket or different socket cases, like if we compare the first bar with the third bar, if we compare the first bar and the second bar, then we can see the difference is minimal. Okay? So the information from this slide is that for OVS DPDK users, we will have fewer contact switches because of the design, the PUMO driver or the data plane design of DPDK. And a cross-socket design, in this case, is not the root cause of contact switches. So finally, in conclusion, this work, we conduct a thorough performance analysis between vanilla OVS and OVS DPDK from a new angle. And we can see that OVS DPDK improves the system performance by first increasing IPC and increase the cache references. And then it decreased the cache misses by utilizing the software prefetching mechanism, and also decrease the TLB misses by using huge page. And also contact switches is less because of the user space driver. And we also studied the multi-socket platform. This multi-socket platform may lead to lower system throughput and less LLC access. So if a cross-socket, in this case, however, it's not the root cause of the contact switches, we can make this conclusion as such. So that's all I have prepared for today, and I'm open for any questions from the audience.
I actually had 3 questions or observations. I didn't catch the packet size for your numbers. Is it like 64 bytes?
Yeah, that's a good point. So we use the default iPerf configurations, so I believe it's using the large packet size.
Like 1500, something like that?
Yes.
Okay.
So, yeah.
And then an observation, in your VM to host, you're kind of understating the benefit, because when you think about it, you have to go VM on one machine, OVS DPDK on that machine.
Right.
Then you have to go OVS DPDK on the other machine and back to the VM host.
Right.
And you're only measuring one benefit. There's always 2 OVS DPDKs in the sequence, right? So it's actually better than what you said, I think.
Right.
All right.
Yeah.
And then the last question was, you showed like 10 gig, 11 gig between VMs in a scenario on the same socket or dual socket. But if you've got 40 gig links coming in, isn't that a huge bottleneck? I mean, you come in on a 40 gig link, and then the only VM to VM you can do is 10 or 11 gig. How do you solve that? How do you improve that when we're going from 40 to 100 gig on that?
We actually didn't have run any experiment on the 40 gig and 100 gig, but it's definitely on the next step to do it. But as I can see, the data, performance data should be consistent in either of these cases because of the design itself, I believe, but that's my assumption.
But your VM to VM is not limited by your 10 gig pipe, right?
Oh,
VM to VM is pure memory.
That's only the VM to host.
So that's the maximum capacity for that machine.
Right, right.
So if you've got a service chaining application where you're going firewall to, or load balancer to firewall to IPS to QoS or something, then you've got multiple 10 gig connections between the VMs. So there's also a question, what if you run multiple VM to VM communications? Does it drop below the 10 gig? Or so another area.
Right. That's a good point. And we definitely would like to see that. Thank you.
It would be really interesting to get some numbers on the CPU utilization and the power consumption of the two, because that's an area where you have a lot of indirect costs that are not directly easily measurable.
Right. Actually, we are conducting another experiments. We have a plan to do the power analysis, and also CPU utilization is not difficult, but for the power consumption, we need to do some hardware configurations. But right, it's definitely interesting to see that result.
I have a question here. So this is about your multi-socket tests with OVS DPDK. So in that, can you tell us how you did the huge page mapping? Was it pinned to one particular socket, or did it even matter?
I'm sorry.
So when you're using 2 sockets, so where do you pin the huge pages? Do you pin it on both the sockets equally, or does it matter?
So your question is, does it matter if we are using many more sockets?
Yes. So looking at your LLC misses or in the same socket and different socket, the numbers are quite comparable. I'm wondering if you did even huge page allocation in both, which is what by default, when you allocate huge pages, it picks it from both the sockets, right? Did you do anything to pin it to one particular socket? Do you see any difference in that?
Oh, you mean, do we create huge page across different sockets? That's a good question. We actually create huge page within the same socket if running the VM. But I I don't think we did that across socket. But if that's something interesting to see, we can do that. Yeah.
Thanks.
I have one question here regarding on the iPerf model that you were seeing on the VM to host.
Yep.
The diagrams of the iPerf test setup before the performance.
Yep.
So I did see, can you go to the page slide with the diagram where you have the host to VM?
Mm-hmm.
Yes. So I'm just wondering, why do you run the iPerf server on the host instead of running it iPerf server in the VM with the OVS DPDK?
Actually, we did both.
Oh, you
Either
did?
way, yeah.
Okay.
Yep.
So does your result represents both scenarios?
Yes, it's consistent.
It's consistent?
Mhm.
Okay, thank you.
All right, if no more questions, I'm glad to talk with this research offline. And thanks for your attention.